notice, and this is a typical copyright. We continue with mathematics syllabus for CSEC 2018 to 2027. Schedule of videos, sections 1, 2, and 3. All 51 of these videos have already been published on YouTube in their entirety. Section 4, measurement. All 17 of these videos are completed, but only 5 are published in their entirety on YouTube. We are now at section 5, statistics. This is the 13th of 18 videos. After that, we still have to do algebra, followed by section 7, relations, functions, and graphs, section 8, geometry and trigonometry, and finally section 9, vectors and matrices. This schedule is no longer valid. It has to be adjusted as I am far behind schedule as of now. Note that in this and the next video, that is video 13 and 14, I will skip most of the usual introductions. So right now we are here, objective 10 in section 5, statistics. This is part A, video 13. And we still have to go up to objective 14 to complete this section. As you can see here, we have reached up to this point. All of those have been completed and published on YouTube. Those 4. These others are only partially published. I am here at 5.10 part A. This is video 13. And once it is finished, I will publish it in its entirety on YouTube. Video 14 is the second part of this objective 10. Previously, I had said that I had divided the section into 17 videos, but because of what happened here, I had to split that objective into 2 videos. So now we have 18 videos. Objective 5.10a, analyze statistical diagrams. And to do that, we have to find mean, mode, median, range, quartiles, interquartile range, and semi-interquartile range. We also have to look for any trends and patterns in these statistical diagrams. So previously, we were given data and we had to prepare graphs. And the first part of this objective, we now have to do the opposite. Given a graph, we have to find mean, mode, median, range, quartiles, interquartile range, and so on from the graph, the diagram. Since there are many different types of graphs based on the 3 types of data we already considered, raw, ungrouped, somewhat raw, and grouped, and then we have grouped, we will limit ourselves to just 6 such graphs in this objective. See the next slide as a reminder. Recall this when we said raw, ungrouped, over here, totally grouped, and then this one in the middle here, which is ungrouped, but is not totally raw. So ungrouped, but not raw. So we will look at 2 examples of that, 2 examples of this, and 2 examples of this in this video and the next one. As I said, we will limit ourselves to just 6 such graphs. This objective also includes trends and patterns. Therefore, we will first consider some general trends and patterns for graphs. Then we will get back to these 6 graphs I mentioned up here. Trends and patterns in graphs generally. So if we have this data here, I am going to produce a graph from that, which looks like this on the right here. So principle 1, direct proportion. As the independent variable increases, that is the x-axis, as this increases, so does the dependent variable, the y-axis. When the graph is a straight line that slants upwards from left to right, you have direct proportion. The actual proportion is obtained by finding the gradient of the graph. It is a straight line graph. And to find the gradient, you divide the increase in y by the increase in x. In your math class, as we will learn later, y2 minus y1 over x2 minus x1. So let us construct a right triangle like what we see here, making sure that we are using at least half of that graph, and we will find the increase in y and divide it by the increase in x. So the increase in y, we are starting y here at 20 and we are going to 80. So that would be 80 minus 20, which would give us 60. So from here to up there is 60 meters. And the increase in x, we are starting here, that's x there, which is 2. And we are ending up here, which is 8. So that red line there, that's the increase in x. So 8 minus 2, that will give us 6 seconds. So then we'll find a gradient by dividing the increase in y, which is 60 meters, by the increase in x, which is 6 seconds, and we get 10 meters per second. Keep in mind that 60 divided by 6 is not just 10, as we will get in our calculator. It is actually 10 to 1. So direct proportion, and the rate is 10 meters to every 1 second. Review. We are now going to look at interpolation and extrapolation, but we have done this before, so this is just a review. Interpolation finds values within the range of known data, while extrapolation guesses or estimates values outside that range. Interpolation is generally considered more reliable because it makes fewer assumptions about the data. So let us say we have this graph here. Interpolation finds values within the range of known data. Example, how much time will it take to cover a distance of 64 meters? So we go up here to 64 meters, come across until we touch this graph, then come down here, and we get our answer at that point, which is 6.4 seconds. Notice that is within the known data. And we could go the other way around. We could be given the time here and then find the distance across here. But it is within the known data. Extrapolation finds values outside the range. For example, what will be the distance at 11.2 seconds? Well, we come here to 11.2 seconds, draw a line going up, and we have a problem here because we are not touching the graph. So we will have to extend the graph beyond the known data using broken lines, dashed lines, following the pattern of the graph. In other words, if it's going straight up, we will draw that broken line going straight up. So it looks like this now that we have here. Now that we have that, we could draw a line coming across here, and we have our answer at this point, which is 112 meters. But that is outside the known data. Let's further explore this. Suppose we have only this part of the graph. Interpolation and extrapolation are methods used to estimate values based on known data points. So interpolation finds values within the range of known data. That is, given anything in here for distance, we can find the corresponding time down here, or the other way around. Given any time from here to there, we can find the corresponding distance on this side within known data. Extrapolation finds values outside the range. So down in here, we don't have data here for this graph, or over on this side up to there. So what we will have to do is extend the graph as you see here, as you see here, and up here. Next, principle 2, inverse proportion. This time, as the independent variable increases, that is the x-axis, the dependent variable on the y-axis decreases. So as one increases, the next one decreases. So it is inverse. So we look at this graph here. As this axis increases, notice this one here decreases. So anytime you have a graph that is a straight line that slants downwards from left to right, you have inverse. So the gradient will be the proportion, which is y2 minus y1 over x2 minus x1. So let's find a gradient here. Notice this time y begins at 80 and ends at 20, and x begins at 2 and ends at 8. The increase in y, notice I am saying increase in y, is 20 minus 80, and you get negative 60 meters. That negative is important. The increase in x, on the other hand, is 8 minus 2, and you get 6 seconds. So if you find the gradient, you have to divide negative 60 by 6, and you get negative 10 meters per second. Now, anytime you get a negative gradient, it indicates an inverse proportion. That is to say, the graph slants downwards from left to right. Principle 3, a larger absolute gradient indicates a greater rate of change. And I am using the word absolute here because that will become important when we deal with inverse proportion. So we have direct proportions here. We have 3 graphs. The gradient for each one will be increase in y divided by increase in x. So let's take a closer look at this. If I draw that purple line there coming down, and we find a gradient for each part here, this is a right triangle. So we can find a gradient for each part here. The gradient for this line here is 25 divided by 5, which is 5 meters per second. That is 25. That is 25 on the y-axis divided by 5 on the x-axis. All of them will be 5 on the x-axis. And so we get 5 meters per second. This next one here is actually 50 divided by 5, and we get 10 meters per second. And this other one here is 75 divided by 5, and we get 15 meters per second. So as you could see, the gradient here is 5. The gradient here is 10, which means that that green line is twice as steep as this blue line. And the gradient for this red line here is 15, which means that that red line is 3 times as steep as this blue line. Notice that negative 15 is smaller than negative 5. But if we take the absolute value, then 15 is greater than 5. For each straight line graph, the rate of change is constant throughout. So this blue line, it doesn't matter where you consider the rate of change or the gradient, it will always be 5. And the same thing applies to that green line and the red line. Now, if we look at the inverse proportion, and we get a right triangle here, Now, this time, the increase in y is negative 25. The increase in x is 5. So if you divide negative 25 by 5, you will get negative 5 meters per second. And the same thing applies for this one here. If you divide negative 50 by 5, you will get negative 10 meters per second. And similarly for this one. Now, I am using the word absolute here because we will now ignore those negatives for comparison's sake. So we will just consider this one as having a greater gradient, 15, than this one down here, 10, than this one down here, 5. We are using just the absolute values because you know that negative 15 is less than negative 5. So we will ignore the negative when we are comparing the steepness of these graphs. Principle 4, curved line graphs indicates a varying rate of change. So far we have been looking at straight line graphs. Now we will consider curved line graphs. So I will use the data in this table to prepare a graph, and I get this graph here you see on the right. Now it is not a straight line. So how do you interpret such a graph? Now, can we still use gradient as increase in y over increase in x? Yes, with one little adjustment. We will draw a tangent at a specific point to touch the curve and then find the gradient of the tangent. So as you could see, we have a blue line here, which is a tangent at this point to that curve. We have a black line here, which is a tangent that touches the curve at this point. You can already see that that blue line is steeper when compared with this black line up here, which means that the gradient of the blue line will be greater than the gradient of the black line, which means that the rate of change is changing as we move from one point to the next. So the tangent to a curve is a straight line touching that curve, but not cutting or intersecting the curve, just touching it. The gradient of the tangent represents the gradient at that point of the curve. So let's call this principle 4a. If steeper to begin with, but further to the right, it begins to flatten out, then the rate of change decreases as the x-axis increases. In other words, as you go this way, this one here begins to change rapidly, but later on, it doesn't change as fast. So if you find the gradient of this tangent, we get 8. We find the gradient of that tangent, we get 2.8. So obviously, here, down here, you have a greater rate of change than up here. So as we move along this graph from below here, 0, 0, and go all the way up here, we have the rate of change is decreasing. Now the change is still increasing, but the rate of change is decreasing. Now if the graph looks like this, it is a curved line. If we consider this tangent down here, it's not very steep in comparison to this tangent up here. So what happens is that one is steep. This one is not very steep, which means that the rate of change gradually increases as we go along this way until it reaches its highest value up here. So the rate of change changes. So let's consider this to make it a little clearer. We have now the three graphs together. If we were to draw two perpendicular there, this red one and this blue one, you will notice that if we were to go along this brown line, the rate of change remains the same throughout. However, if you consider this blue line up here, you will notice that in the first 4 seconds, You had a lot of change, all of that. And then in the next 4 seconds, you had this change. So not as much. And finally, in the last 4 seconds, you had only that little piece of change there. So you could see that you have a decreasing rate of increase. Overall, this y-axis is still increasing, but it is not increasing as fast in the latter part of this time than in the earlier part. So you have a decreasing rate of increase. Let's consider this green line down here. Notice in the first 4 seconds, only that velocity changed. In the next 4 seconds, the velocity changed by that much. And finally, in the last 4 seconds, the velocity changed by this much that you see here. So you could see an increasing rate of change of velocity. So A and C show varying rates of increase. They're both increase, but varying rates. This blue one is showing a decreasing rate of increase, and this green one, an increasing rate of increase. Now we will consider varying rates of decrease. So let's look at this graph here. This one here, B, has a constant rate of decrease. For every 4 seconds, for this brown line here, graph, you have a constant rate of decrease. So 4 seconds will take us there, there, come across here. You have that amount of decrease. The next 4 seconds brings us here. You have this amount of decrease. And the last 4 seconds, you have this amount of decrease. So you could see an equal amount of decrease. That's for this brown line here, constant rate of decrease. Let's consider the blue line now. For this 4 seconds, you have that amount of decrease. For the next 4 seconds, you have this amount of decrease. And for the last 4 seconds, you have that amount of decrease. So that was a decrease in the first 4 seconds. Notice you have a decreasing rate of decrease. That's for the blue line. Now let's consider the green line. For the first 4 seconds, you have that amount of decrease. For the next 4 seconds, you have this amount of decrease. And for the last 4 seconds, you have all of that decrease. So you could see an increasing rate of decrease. So if you have a flatter line early in the time on the x-axis, it means a smaller rate of change that later increases. And of course, if you have a steeper line at the beginning, like here, it means a greater rate of change that later tapers off. To help you better understand this concept, we will change the y-axis to money in the next slide and the time to months. So we have this now in money, and we have this time here in months. Let us say you have 3 departments of a large store, and department B has $55,000 to spend in 12 months. The supervisor there divides that amount into 12 equal parts and spends $4,583.33 every month. So in the first 4 months, that person would have spent that amount. In the next 4 months, that person would have spent that same amount. And in the last 4 months, the same amount. which works out to the same amount per month. So a constant rate of decrease. Now let's deal with department C. Same amount of money, 55,000, to spend in 12 months. She spends much less than this other person here in the first 4 months, which amounts to that amount, first 4 months. And then about the same as this person here in the next 4 months, which is this. And finally, much more for the last 4 months because now she has this amount of money to spend. So you could see this person starts out slowly, then increases a little more, and then the greatest increase here. So you have an increasing rate of decrease. Overall, the amount of money is still decreasing. But as time goes by, the amount of decrease is increasing. Now let's look at department A. Same 55,000, same time to spend the money. This time he spends much more than this person up here per month. So in 4 months, spends that amount of money, more than half of the money. And then for the next 4 months, this amount, so that the last 4 months, he has only this amount of money to spend. I'm not saying that anybody is better than the other person. The supervisors determine how they need to spend the money they have to spend. And all of them may be totally valid. But I hope you understand the concept of what may seem like apparent contradiction when I talk about an increasing rate of decrease and so on. Principle 5, horizontal or vertical graph. Now remember, we are just looking at trends and patterns of line graphs. So if you have a horizontal graph, like this, if you try to find the gradient of that, which is the increase in the y-axis divided by the increase in the x-axis, you notice that the x-axis changes as we go along from left to right by that amount, whereas the y-axis stays constant. So if we attempt to find the gradient of that line, y2 minus y1 divided by x2 minus x1, we get 0 for the increase in y. There is no increase in y, divide by 10. And so the gradient is 0, which means that there is no change taking place in that graph. Conversely, if the graph is vertical, like this one here, remember gradient is increase in y divided by increase in x. So the y does change. The x has no change. It goes straight up. So as I said, so the y-axis changes, the x-axis has no change. So if we were to find the gradient, increase in y divided by increase in x, the increase in y is 100 from here to there, but the increase in x is 0 because you start at 6 and you end at 6. So how do you divide 100 by 0? And you learned this a long time ago that you can't divide by 0. So what do you get? You write down the sign here. A sideways figure 8 is considered a mathematical symbol representing the concept of infinity. In other words, you get an answer so large, you can't write it down. It was introduced, this concept of this figure 8, in 1655 by the English mathematician John Wallis. You don't need to know this piece here. You do need to know that if you divide by 0, what you get is infinity, and you write it like that. Now, if we are doing a speed time graph of somebody running a 100-meter race, this is what we would like to happen. In the first second, they reach a speed of 10 meters per second, and after that continues for the remaining time. That is ideal. What actually may happen is something like this. For the first few seconds, they increase in speed and pass 10 meters per second, maintain 12 meters per second, and gradually slow down a little until the 10 seconds are finished. This may be more typical of what actually happens. Now, principle 6, the versatility of line graphs, including line of best fit. Now, if you are using a formula to plot points on a graph, you will most likely get a smooth line to join all those points. But in real-life research and experimental work, the data points do not all line up in a straight line or a smooth curve. In such cases, a line of best fit has to be used. That's one of the advantages of using a line graph. So out of these graphs that we had to, and charts that we had to learn about, the line graph seems to be the most versatile. And in your SBA, you may consider using this as well as pie charts and maybe bar graphs. So the most versatile, the line graph. And as I said, think about interpolation, extrapolation, gradient, and line of best fit. You can do all of those with line graphs. But with the others, you may not be able to do even one of those. Now, I am not going to deal with line graph again. Already looked at those general principles. If you want to find out more about line graph, I do have 3 videos in the physics section, 3 videos in this same YouTube channel that totals about 90 minutes. As you could see, physics 23, part 1, line of best fit, part 2, more on line of best fit, original point fix, and then part 3, extrapolation, interpolation, and more on line of best fit. So 90 minutes, 3 videos on line of best fit if you want to learn more about that. And it doesn't matter if you are not doing physics. The principles are the same in whatever field you are studying. We will just look at 2 examples as a reminder of what was covered in those videos. This was one, radioactive decay curve. Looks like this. It is a smooth curve, but notice we missed some points here and there and there. So we try to get a smooth curve among those points. Line of best fit. You can't do that with the other type of graphs, like pie chart or a column chart. And then monthly income. This is an example we will look at later on in the same video when we consider pie chart and a column graph. So you have this line graph here, but what you can do with that line graph is this, a trend line. But really, this line graph is the most versatile. And now, for the rest of this video, we will consider 2 specific types of graphs, pie chart and the column chart or column graph. Example 1, pie chart from raw ungroup data. So we have this table here on the left. It is arranged in descending order of sales. From that table, I will prepare a pie chart, which looks like this. From that pie chart, we will try to find mean, mode, median, range, the various quartiles, interquartile range, and the semi-interquartile range. We will also look for trends and patterns. Note that in this objective, objective 5.10, you will not be given this table that you see here, just the chart on the right here. But I use that table to produce this chart. And from the chart, we will try to get all these things down here. can these be found from the pie chart? Now let's begin with me. Well, we are told that the total sales is $213,000. And since it is 12 months, we divide 213,000 by 12 and we get $17,800 per month as the mean, as an average. Let's also look at the mode. We see here May and February 5%. We see March and April 6%. We see June and July 7%. So we actually have three modes according to that pie chart. 5%, we will multiply it by 213,000. 6%, we follow the same steps. And so we get the modes as being 10,600, 12,800, and 14,900. So we can list those two here, mean and mode. Next, we will look at median and range. Well, this line here, on the left-hand side, you have the least, and on the right-hand side, you have the most. If we count going this way, 6th position, we will reach here. Or if we count going this way, the 6th position, we will reach there. So obviously, our median will be the average of July and August. So 7 plus 8 would give you 15. Divide that by 2, you get 7.5%. Carry that to a decimal. Multiply that by 230,000 and we get approximately 16,000 as the median, which is Q2. So somewhere between here. We are just referencing this table to make sure we are on the right track. But remember, you are not given that table. You would only have to work off the pie chart. The range, well, 5% of that will be the least. 14% of that 230,000 will be the most. You can find 14% and then 5% and then subtract them, or you could subtract the percentage to begin with. 14% minus 5% would give us 9% as a decimal, that's 0.09. Multiply it by 213,000 and we get 19,000 as the range. So up to this point, we have these four: mean, mode, median, and range. Obviously, next we will deal with the quartile, the first quartile and the third quartile. We already got the second one as the median. So we got Q2 already, the second quartile, which is the median, which is here. If we count from there, coming this way, we will get 1, 2, 3, 4, 5, 6. So somewhere between here is the first quartile. So the first quartile will be 6 plus 6 divided by 2, 6%, which is 0.06. Multiply that by 213,000 and we get 12,800 as Q1, which will be somewhere in between here if we keep track on that table. Now for Q3, if we count this way, 1, 2, 3, we will reach here. Or if we go that way, 1, 2, 3, we will reach here. So we'll have to find the mean of those two. 10 and 11, that will give us 21. Divided by 2, we get 10.5%. Carry that to a decimal. And so we multiply 213,000 by 0.105 and we get 22,400, which is somewhere here if we keep track on this table. But remember, I told you, you're not given that table. So up to this point, we have mean, mode, median, range, first quartile, third quartile. Okay. We need to now deal with the interquartile range and the semi-interquartile range. If we have reached this far, those two are extremely easy. So the interquartile range is the difference between Q3 and Q1. And this is Q3, that is Q1. We subtract those two and we get 9,590. And the Semi-interquartile range is 1/2 of the interquartile range. So all we need to do is divide this 9,590 by 2, and we get 4,790. So as of now, we have these 7 things from that pie chart. If an online calculator is used, how do our answers stack up with those from the online calculator? So let's double check this on the online calculator. So this is the pie chart we are using. These are the information we got. That's the online calculator. For December, 14%, that's percent, November, 12%, and so on. I entered that information in the online calculator, press calculate, and since we are using percentage here, to match that with what we have over here, we will have to multiply the percentage by 213,000. As I said, we have to multiply by 213,000. So mean is 8.333. If we multiply that by 213,000, we get 17,800, which is exactly what we got from the pie chart. The median, 7.5 from the calculator multiplied by 213,000, approximately 16,000, which is exactly what we got from the pie chart. The second quartile, which is the median, which is what we just looked at, is the same, 16,000. The first quartile, 6%, multiply 6%, which is 0.06 by 213,000, and we get 12,800, which is this first quartile here, exactly 12,800. So far, we are doing fairly well. Our answers from the pie chart correspond exactly with those from the calculator. Let's continue with mode, multimodal. As you see here, we have 3 modes, and the online calculator says yes, 3 modes, 5%, 6%, 7%. When we convert that into sales, 10,700, we actually have 10,600, not too bad. 12,800, yes, exactly 12,800, and 14,900, exactly that. So the modes correspond. The range down here, 9, multiply that by 213,000 and we get 19,200. We actually have 19,000 from our pie chart, which is extremely good. And then Q3, 10.75%, convert that, the sales, and we get 22,900. We actually got here 22,400, not too bad. Interquartile range, 4.75%, multiply that by 213,000, and we get 10,100. Over here we have 9,600. Not too bad. Semi-interquartile range, from the calculator, 2.375, multiply by 213,000, we get 5,100. Over here we have 4,800 almost. So our answers are very close to the online calculator. So we're not doing too badly using a pie chart to find these 7 aspects of the pie chart. So can these be found from the pie chart? And we just found out, yes. This is what we got, and they all correspond very closely with the online calculator. We did not have to use this table, only just for reference. One last thing, trends and patterns. So is there any trend or pattern that we can see here from this pie chart? Yes, we can see that the sales were lowest in the months of February and May. We can see that, lowest, 5%. We can also see that the sales kind of picked up in the month of November, here to 12%, and it reached its highest in December at 14%. So we can see those two trends or patterns from that pie chart. And there are others, but those two will work for now. There are many other variations of this question. For example, you may not be given the total sales. You may just be given the sales for September, say 23,500. But if 11% is equal to 23,500, then you can find all the others. If you find this video useful and interesting, please like and share. That is to say, like and share. You may also consider subscribing to this channel. Example 2, column chart from raw ungrouped data. So what I did, I used the same data as I used for the previous pie chart, but in this case, it is not sorted. So I'm using this table here to prepare the column chart or column graph, and we will follow the same procedure to find those features from the graph. So this is the graph we have here. Sales in thousands. So for example, this would be 20,000. This would be 10,000. Now this is more difficult because it is not sorted, but we can still derive those pieces of information from it. Of course, we will have to sort it. But since the graph is already there, we'll have to find another way of sorting it because the graph is. As we go along, we will compare our answers from this bar graph with the pie chart that we just did previously. Remember, we are using the same data. However, from this bar graph, it is easier to see a pattern. For example, in this red box here, you can see that from February to August, the sales were low at less than 17,000. That is 17,000 when compared with the rest of the year. You can clearly see that. You couldn't have seen that clearly from the pie chart because the months were mixed up. You can even make a prediction. In January of next year, sales will drop by about 9,000. That is to say, from here, which is 29,000, to here, which is 20,000. So about 9,000. That's a prediction. Followed by the lowest drop in February, which is the lowest drop here. That is assuming that things continue the way they did for this year. Next year, we can expect that. So now let's deal with range. This is the highest, and this is the lowest. This green line here shows the range, which is 29,000 minus 10,000, and we get 19,000. So from here to there is 19,000. That's the range. How does that compare with the pie chart? The range? Yes, we got 19,000 with the pie chart as well. Next, let's deal with mode. Now, in this case, there is no mode. As a matter of fact, as I said, working with this graph as is, without the data being sorted, is a little more difficult. So we may have to rank the data on the graph itself. So this is the highest, 1, and then 2, 3, 4, 5, and so on. 6, 7, 8, 9, 10, 11, and 12. So even though the graph wasn't ranked to begin with, we have just ranked it because we need to rank it to answer the questions we need to answer. So that's 12. If you look carefully, you don't have any two of those bars on the same level. So we have no mode. The online calculator may actually say that every single one is a mode. But for now, we know, based on what we are learning, is that there is no mode, irrespective of what the online calculator may say. Remember the pie chart, we had 3 modes. The bar graph says no mode. Next, let's deal with median. The middle value, Q2. We want to find the middle value. 1, 2, 3, 4, 5, 6, and this is 7. So obviously, the middle value is somewhere between 6 and 7, between the 6th highest and the 7th highest. That is to say, that 7th highest is 15,000, the 6th highest is 17,000. So halfway between there, this line here, that line there, that line here, will be, this line here, will be 16,000. We don't have to do any calculation. We could just read it off. So Q2, the median, is 16,000. How did that compare with the pie chart? Yes, from the pie chart, we also got 16,000. Let's deal with mean. Now, this is a little tedious, but it is not difficult. This value here is 20,000. This next value here is 10,000. This next one here is 12,000. So we have to take all of those individually, add them up to get the total sales, which is 213,000, and divide by 12, and we get 17,750, which is approximately 17,800. And for the mean, from the pie chart, we actually got 17,800. Next, we will look at the quartiles. The first quartile and the third quartile. We already found the second quartile because that was the median. So the first quartile I have here is 12,500. Now, how do I get that? This is the sixth highest, which means that is the seventh highest, that is the eighth, that is the ninth. So those three going down from the median, and this 12, 10, and 11 are three coming up from the lowest. So obviously our answer will be between 9 and 10. Between the 9th position and the 10th position, which is between 12 and 13, which gives us 12,500. That's Q1. So Q1 we had here was 12,800. From this bar graph, we got 12,500, which is very good. Now let's deal with Q3. So that's 1, 2, 3. So it's between the third and the fourth. Because remember, 1, 2, 3, 4, 5, 6. That's the top half. So we want to find what is halfway between there. So it's between the third and the fourth. The third is here, which is 24, and the fourth is here, which is 22. So we add 24 and 22, divide by 2, and we get 23,000 as Q3. 23,000 as Q3. Up here for the pie chart, we had 22,400. So our answers correspond fairly well. Next, we will deal with the interquartile range. That is the range from Q1 to Q3. So this is Q1, that is Q3. 23,000 minus 12,500, we get 10,500 as the interquartile range, the middle section of our data. And over here, we had interquartile range as 9,590, 9,600. And here we have 10,500. We got some discrepancy there, but nothing to worry about. Next, we will look at semi-interquartile range. So if this is the interquartile range, semi-interquartile range would be half of that. So the interquartile range was 10,500. The semi-interquartile range would be half of that, which would be from there to there. Half of the interquartile range, which is 5,300. And over here we had 4,800. So it's close, but not exact. And we didn't expect them to be exact. Now, it would have been easier if we had ranked the data first for this column graph, like this: highest, the lowest, then we could have checked our answer as we go along and find the median somewhere here, and so on. So we would have gotten a graph like this. Now, don't be fooled by this apparent pattern here. You know, looks like it decreases in an orderly manner. Don't be fooled by that because the months are all jumbled up. The months are all jumbled. We cannot determine a trend here. Now, that should suffice for raw, ungrouped data. So we looked at two examples for raw, ungrouped data. Let's go compare the answer for that from the column chart with the online calculator. January, 20%, February, 10%. Let's see what we got. This time we'll have to multiply by 1,000 because these are percentages and we need to carry them to sales. So let's begin with mean. 17.75% multiplied by 1,000, 17,800, which is what we got from the column chart. Median, 16 multiplied by 1,000, which is 16,000, is what we got from the column chart. Q2, which is the same as median, 16,000. Q1, 12.25% multiplied by 1,000, which is 12,300 approximately. Here we have 12,500, very close. Q3, 23.5% multiplied by 1,000, 23,500. And here we had just 23,000. So we are a little off. Reasonably good so far. Let's look at the rest of the information we wanted. Range, 19,000 here. Range, 19,000 here. So it's exact from the column chart and the online calculator. 19,000. Mode, now here's the problem. The online calculator gave us every single piece of data as mode, whereas we said there was no mode because we don't have two or more of the same thing. So we will ignore the online calculator for now. All or none, actually none. Interquartile range, 11.25 multiplied by 1,000, 11,300, and we got 10,500, so we are somewhere off from that. And finally, the semi-interquartile range, we got 5,300, and the online calculator, which calls it quartile deviation, multiply that, and we get 5,600, so we are not so far off. So basically, we did reasonably well when we compare our answers with those from the online calculator. 5.10a, analyze statistical diagrams, and we look at those aspects of two charts or graphs. And that brings us to the end of video 13 based on objective 10a in section 5.